Do you want to know how people are using drone-based LiDAR in DOT? Well, in this video, we have a unique offer where this was a video with our partners Velodyne on how this technology is being used in construction and transportation today. So in this video, we are going to cover the base technology and how this differs from other technologies out there. We're also going to look at the Velodyne product and how it differs and what advantages it actually has in the drone-based market. We're also going to go into how to plan and how to get the most value out of your LiDAR system when you step onto a job site. And lastly, we're going to break into the business case of a LiDAR system actually being used on a construction plant today. So let's get started with the training, and I hope you enjoy the findings we have. All right, let's go.
So without further ado, first off, hello, I'm Dan Aver, and so I am the one of your speakers today. I am the owner of Mapping Operations Data Unmanned Solutions. I know, long name. And we'll talk about what we do in a second, but for the folks that don't know who I am, I've been in the drone industry for over 15 years. I've run special op forces drone deployments all over the Middle East. I fielded various military systems. I was one of the project managers on the MQ-9 Reaper program for selling to the Air Force and for military customers. I've been a pilot, attack helicopter pilot for most of my time in the Navy, and the little time that I did, I'm a and then real briefly, so what am I, or what is this company? And basically what we are is a specialty system where we focus mostly on remote applications for mapping. And we're a little different in the fact that we have integration partners, but we do sell the hardware, but we also do rentals. All our stuff is covered end to end, from training and support. We can do the data processing, supplying, and then for our enterprise programs, we even come in and do proof of concepts and business analysis to actually streamline your workflow. Because really for us, at the heart of it, we're all about getting a high return on investment using these types of technology. And then I want to introduce Frank. Go ahead.
Thanks, Dan. So my name is Frank Bertini. I cover the East Coast for Velodyne Lidar for the last 4 years, but I have a background in industrial automation and sensors for about a decade. So selling things into robots, drones, as well as industrial equipment as well. So today we'll be getting into a bit of the LiDAR and also talking about some of the other components that are needed to sort of make it work into a complete mapping solution. And then Dan will be going over some of the more planning and what you have to do once you get on site. All right, so a quick overview on Velodyne. So Velodyne was founded in 1983, so we're actually one of the oldest companies in Silicon Valley. Last year, or 2 years ago in 2017, we opened up our mega factory. So it's 250,000 square feet of manufacturing space now where we're building these sensors. We also partnered with Nikon as a contract manufacturer. So you'll start seeing the quality and the level of reliability, durability of the sensors increase over time with these manufacturing partnerships that we've made. So I talked a little bit about the founding, 1983. The founder is David Hall, and he got his start with subwoofers. So he's always been the serial inventor type of guy in the lab, doing soldering on the electronics, messing around with different gizmos and gadgets. So in the mid-2000s, he got involved with the DARPA Grand Challenge, and that's really what birthed or gave to life the LiDAR sensors. So here you see the original team. It's called Team Dad, and you can see on the roof there, this was some of the original sensors that were used, mostly cameras. They're doing a digital camera technique. They could see some objects some of the time, but Dave really needed something that could see all of the objects all the time, give a full 360-degree representation of the environment. So in 2006, Lidar was invented. See, it's quite a large device compared to what we see today on our small drones, but this first one I think was something like 110 pounds. The motor used to spin around was bigger than the actual sensor device. So we've been able to miniaturize that quite a bit over time. So we started commercial production. There's a picture of our facility here. Lots of different workstations, quite a few different options now for the LiDAR sensors, and we'll get into that, which one to use in which specific environment, which specific application. Let's see, I'm trying to move it here. Okay, so a couple of the sensors that are available now is the puck. We also have an ultra lightweight puck called the Puck Light, only 590 grams, which is great for any aerial vehicle. So we're not just in drones, we're in a lot of different ancillary markets, and the volume of these markets is what's helping drive the price down for drones. So when we sell 1 million sensors into an automotive program, that brings the price down for everyone. So that's something to look forward to in the future, is that the price of these electronics follow Moore's law roughly. So about every 2 years or so, you'll see sort of a step down in price, but also an increase in terms of performance. So when I say performance, things like points per second, we'll talk about that, and also channels, number of channels inside the sensor, number of laser beams that we have. So in our VLP16, that's 16 different channels, 16 laser beams. Okay, so why do we choose LiDAR instead of cameras or photogrammetry for doing this aerial surveying work? A few of the reasons here is it's more efficient, so you can fly over more area faster. It also penetrates the vegetation. You can also do day or night operations. You probably won't be doing a bunch of drone operations in the night, but say it gets close to the end of the day, light's starting to fade a little bit, it's not going to affect your LiDAR data, whereas with a camera or something like that, it would get affected by lighting. So that's something to keep in note. And then it's also great for thin vertical structures. So think trees, wind turbines, really any vertical structure at all. With our multi-beam advantage, you can see around the canopy or the roof line and start to get the side of the building to build up a full map of what you're looking at.
And I want to add real quick on the day-night, where LiDAR has been getting an advantage in weird places is in airport operations where you can't fly a drone during the day. However, when the field shuts down at night and you need to do these surveys, folks have been using LiDAR to map and take advantage of that opportunity to get their data in. So, all right.
That's a good point. Some industries where you have to fly at night due to the downtime. So one of the advantages for Velodyne is that these sensors have multiple beams. So instead of just one single beam that's shooting from the sensor, we actually have a fan of 16, 32, or even more in some cases. So the issue with the single beam is that you get a shadow behind the target that you're looking at. So here in the bottom, you can see I have the sensors pointing in this sort of 45-degree angle. This truck is in the way, so everything behind that truck is going to be in the shadow. You won't be able to see it because the truck occludes the sensor, of course. So the way we combat that is with multiple beams. So instead of having the one beam, again, we have a whole fan of beams shooting out at different angles. So in the VLP16, it shoots at a total of 30 degrees. So it goes from 0 degrees all the way to 30, and each laser is labeled, correctly numbered, and there's about 2 degrees of spacing between each laser. So what that gives us, you'll see, is a fuller view of the targets that we're looking at. So even if the sensor does get occluded for a period of time, gets blocked by this truck here, as you're moving through space, especially with the drone, as you're doing that scanning motion flying over, you get targets at about plus 15 degrees coming at the target. And then as you passed it, you hit it on the back as well on the reverse side. So that allows you to see underneath canopies, underneath roof lines, and around targets. So we'll show what that looks like in the real data here. So this is an image taken doing some roadway mapping. You'll see on the left, single beam LiDAR was used, and you can very clearly see the shadows emanating from the cars. So anything behind there, if there's a fire hydrant or a doorway or any other structures that you might be interested in, they're just simply blocked because you only have that single beam and you're only passing through directly and hitting it at a perpendicular angle. Now with the multi-beam advantage that Velodyne has with our 32 channel sensor, you can see just the level of detail has increased quite a bit. We're also eliminating a lot of those shadows behind the vehicle, and what that does, it allows us to see more objects. So we can start to see the complete size of this doorway. We can actually take measurements of that doorway where we couldn't before because of the shadow. We're also seeing slightly into the structure as well. So if that type of data is important, the multi-beam really allows to see more. It's much more rich in terms of the amount of points you're getting. So again, another example of this. This is a first responder training center. So these buildings get reconfigured in different ways depending on the training session. So say it's some firefighters or EMTs are in here, they may change where the fences are. So this is a test facility and the area is always changing. So they want to take a 3D map of it and start to map out and do some planning on how they're going to organize all of these structures for their next event. So here we're flying over with the single beam scan, and you can see with the scan this very typical scan pattern starts to arise, and that's based on the way the laser is scanning back and forth as you're flying over. So again, that's with the single beam competitor sensor. Now with ours, the multi-beam 3D LiDAR, you can see the point density is enhanced, and you can also see much more of the structure. So you're starting to see the roof line. You're seeing very clear sides of the building, a lot less noise as well. So with post-processing, the image really comes out much more richer, much more detailed. Again, here we show the multi-beam advantage, but here it's against photogrammetry. So photogrammetry is a technique that I think a lot of you guys are similar or familiar with, rather. It's kind of similar in that we're flying over and we're collecting data. However, photogrammetry, what it does is it stitches together all of the pictures. And when you do that, sometimes you get some artifacts in the picture. You can see here on the top right, we used photogrammetry to look at this tree line. Trees especially are very difficult because it confuses the photogrammetry software and it kind of meshes them all together in kind of this amorphous blob. So you can see the tree line is not very detailed, and the house as well. We can see that a house is there. We can take some rough measurements on it. But if we really want to get that detail, we want to see numbers of windows. Maybe we want to do square footage of the roof. We want to take more specific measurements. That's where LiDAR really starts to shine. So we see in the bottom left here, just the richness of detail from the LiDAR. We can see branches, we can see crown heights of trees, we can measure diameter of the trees. So just a lot more detail in terms of what we're getting.
And also you can see how much more of the topography we're getting underneath that vegetation. Where we look at the photogrammetry, that will be, if we make a model, that's all going to be blacked out on the topography. And here, we're getting several points underneath each canopy.
Yeah, that's a perfect explanation and a good note. So since you're hitting at all different angles as you're shooting through the trees, the laser is able to get underneath all those twigs and branches and leaves and eventually penetrate down to the surface. And that's how you collect your surface data if you're doing like digital terrain modeling, DTM, or anything like that. So another popular application for UAVs and LiDAR is with utility companies looking at these electrical overhead lines. So you can see here the trees are starting to encroach a bit on the lines. So with LiDAR, you can take direct measurements and actually measure the tree and know if it's 3 feet away, if that's okay. And then if it starts to encroach, starts to get 2 feet, 1 feet away. Another thing, you can also measure the sag of these power lines as well. So if they get too low, it could propose a risk for an arc or a spark coming from the line. So this is something that a lot of the utility companies are becoming more aware of, and they're looking for new solutions where they can do this faster, with less time, with less people. So the way they did it in the past is they would either take an ATV or they would walk these miles and miles. Now they can do this with overhead LiDAR, scanning down, and take direct measurements of these wires. So a lot of questions that we get from users on the field are things like, how fast do I need to be flying to get a certain amount of point density on the ground? So point density is kind of a major metric that people look at to determine if their data is good enough. So points per square meter, maybe it's 10 points per square meter, maybe it's 100 points. We need to figure out how fast to fly the drone, what altitude to fly the drone, which sensor should we be using from Velodyne to get enough points on the ground. So we've developed this calculator. What it is it's just all of that calculus brought into a mathematical equation. So it's very simple to answer those questions. All those questions, it's just a matter of punching it all in. These are all known values. So we have all that information, and Dan later in the presentation will show you a visual of how this maps out.
Okay, so now that we've actually talked a little bit about the LiDAR sensor specific, I'm going to go more into the integration and into the geospatial part of this. And so the reason why we have this slide up here is, in all the people that we consult with and we talk about LiDAR technology, especially the folks that are doing grants and stuff like that, they get the sensor information and get that pricing, and they think that everything stops right there. But in order to use LiDAR as a mobile technology for mapping, there's a little bit more to that equation that we need to talk about. And I think most people understand that you need a GPS for the location of this, and you need the sensor, but really the heart of what makes this technology viable is the inertial measurement unit and the quality of the inertial measurement unit. So when you're looking at this, the way or the difference that this system works in comparison to, let's say, photogrammetry, for at least for the general photogrammetry that you're seeing in the drone market, is that when you're flying your drone and you're taking pictures, the only thing that you really care about is the general position of the drone, within 3-4 meters, and that you've got good photographic overlap, 60 to 80% overlap, so that you can do structure through motion and to build your three-dimensional model. With LiDAR, it's a little bit different. Where photogrammetry is that passive we talked about, your light source is coming from one place, it's being received in the camera. LiDAR is what we call an active sensor technology. So we measure from the time that the laser energy leaves the sensor, reflects off the object that we're going to measure or the target, and then comes back into the sensor. That's an active measurement. So At every given point in time, we need to know where the drone is, or more importantly, where the IMU is, and what orientation that is in. So the IMU is critical in filling in the gaps between our GPS fixes, refining that area, and then segmenting the time so that every pulse of energy coming out of the LiDAR unit is accounted for spatially or temporally. So that's, that adds a lot of the added cost that a lot of customers, when they come see us, like, this should be way cheaper. And it really comes down to the fidelity of the systems and the fidelity of the sensors that we're putting inside the unit to do the measurement. The other thing with this is that the software that you need, there's a lot of different vendors out on the market, and there's a lot of different ways that they process this data. They're all figuring out the telemetry, they're all working with the IMU, but then depending on which software they're using, they may do the corrections ahead of time so that it makes it survey grade. They may process it all in UTM and then make the corrections to the entire point cloud. But regardless, you're going to need a piece of software to make it geospatially relevant, and that tends not to be very cheap. So, when we sit down, if I'm consulting with somebody, we have to kind of explain this equipment, explain this process, and explain the quality of the decisions of the components moving forward. All right. The other question that we get a lot of is what's the workflow and what's the process? And so when we go into the use case here in a few minutes after we get through some of this theory, you're going to see this workflow come about. And generally speaking, this high level diagram is pretty much what you're going to see, for any drone operation, whether it's photogrammetry, it's LiDAR, it's synthetic aperture radar, it's magnetometry. This is the general steps that you're going to have. The thing that changes is what happens in these little boxes. So when we're planning, at least for how we teach it in our LiDAR operators course, how do you do your overlaps? How much overlap do you need? What's your time and rate? How do you work around obstructions and visual line of sight? A lot of photogrammetry software will keep you at the same altitude. We do not. We have software that follows the map of the Earth because we want to get the microsensing, and we want to be a little safer. And a lot of places aren't flat; they're full of hills. And so, how does that work? The next piece is in the collection. How do you set up this equipment so that you're successful? How does the base station work? How do you have a group of base stations? Control points are always an interesting conversation. And where do you put them? And how many do you need? It's not as much as photogrammetry, but depending on the level of accuracy that you want, you're going to want control points, or you're going to need control points to validate the data if you're going to follow ASPERS guidelines. And next would be the post-processing, and this is where things get really different from photogrammetry and other photo processing techniques, in the fact that it's a lot faster, and we'll talk about that here in a few minutes, but we're really fusing pure digital data together. We're doing time stamping, GPS fixes, inertial fixes, and LiDAR measurements, and we're fusing that all together and then going through a clip, clean, and filter technique, which we'll kind of talk about here more in a minute. And the last piece would be, now that you've got that first initial piece of data, now how are you going to translate it or morph it into actual business intelligence? Whether you're doing blueprints, plans, models, this is, okay, how do we actually take a LiDAR point cloud and move it over? Now that should be, for the most part, very similar to what you're seeing in photogrammetry. It's just you're getting it a lot quicker. All right. Okay, so with mission planning, probably the first thing is the collection plan or the flight plan. And, part of this is, with the FAA rules and stuff like that, how are we going to conform to the current regulations? How are we going to operate safely? So that's one of the first things we look at. But then the next thing is our collection requirements. And I think our approach has been a little bit different based on, my time in the service, where when we deal with aircraft back in the day, we'd be getting a sensor and it may not be everything that we wanted, but we still have a requirement. In this particular case, we have a data deliverable that we need to achieve. And so we now need to change the way that we fly so that we get the optimum amount of efficiency or quality out of that sensor to achieve that objective. And the same thing is here true with drones. With a LiDAR system, there's a variety of different LiDARs out there. And so you have to fly a little bit differently for each one. And you will show that in the example here, so that you get the right quality and, more importantly, you get the right efficiency. Because I can fly really, really slow and get too much data, and I can fly really, really fast and not get enough data. And the trick is knowing where that sweet spot is. And then the field plan, is like how you're going to set up your site, how you're going to get there beforehand, or how you're going to beforehand show up and orchestrate this, and coordination with your survey teams, your safety teams, and how are you actually going to set up those control points. Especially if you're going to do LiDAR and imagery to combined, you don't need as many control points for photogrammetry with LiDAR. But again, the more accuracy that you want, the more control you want. The more professional you are where you have to certify the data, the more control you want. So I know there's a misnomer in the market, and some of the various vendors out there are like, well, you don't need control points. And they're right, you don't, but you do need if you want a quality product. And so when we teach our courses, we really talk about control, as an option, but then understanding what the trade-offs are, so that you're efficient with your time rate in the field, and you get the quality data that your customer is going to want to buy. And then I'll briefly touch on, because we'll talk about this in the scenario, your emergency action plan. So a lot of drone operators will, if they have an emergency action plan or a safety management system, it's usually a book on the shelf. Emergency action plan, at least for our insurance company that works with us, is a must. And it's not just having a safety management plan where you know the general risks and your emergency procedures. It's also identifying the risk of each job site that you're on. So I'll talk about it briefly in the next in this scenario on how I actually had very specific mitigations for risks that I identified before I even got to the job site. And it's not just worrying about the FAA, it's not worrying about keeping people safe, it's also worrying, if you have a $60,000 to a $500,000 sensor out there, covering that financial loss. So those are all three are very important on talking that. So we'll cover that here in a few minutes. Okay, and I threw this in briefly at the last minute because I realized we were talking about LiDAR on a drone. I went, I hadn't talked about drones. It tells you how really unimportant they are in the scheme of collecting the data, but they do have an important role here in understanding that these are the chariots and make it time efficient, but only when combined with a sensor. And so in general, we have three different classes that we look at here. We have the compact, which we call the mini. So that's our VLP-16, which we could have used on this job site. We just didn't have one available. And it's perfect for about 18 minutes, highly portable. We have people that take them all over the place in the back of their car. So it makes it competitive with the ease of the photogrammetry. However, you're not going to be doing big job sites with this. This is 100 acres in a day, something like that. Maybe 200 if you're really efficient. But it has its place in the market. The problem with this is it's highly tailored to that airframe, and then we have to, because we're making it so light, we have to tune to the next airframe and the next airframe that can support it. This is about as small as we can go right now in the current state of technology. Then we have the Flex series here, or the Flex, and right now we're showing it on an M600, but this is something that can do about 10 pounds. This sensor configuration is allowed to move from car to boat to backpack to vehicle, all in the same setup, So it has a really good return on investment. But again, when you're dealing with battery technology, you're looking at 23 to 30 minutes. So as you start to go up and climb into more sophisticated, more expensive sensors, you're going to want to increase the amount of time that you have the aircraft into the air, because it's all about time rate analysis at that point. However, for this scenario, we actually did use the M600. It's the most affordable on the market, and frankly, it's a really good drone for the price point. Now we have our new line here. This is just coming out. It's not even on our website yet. We have a comparable that we do sell with some of our partners. And this one here is a gas hybrid. What's important here, like we just talked about with the Flex, is how do we get up there and maintain more time? And how do we get more sensors up in the air? So with a 28-pound payload, this one's rated for 120 minutes. You know, at that point, you're approaching 500 acres to 700 acres into a flight, depending on the quality that you want. And now that starts to make you competitive with the aerial market, because you're able to do a lot more. You're on demand versus having to plan things out like the aerial guys do. And so if you're starting to deal with more sophisticated sensors, at that point you want to cover as much area as possible. So it really has to do with the efficiency that you're going to provide in the market. Okay. Interesting. Somehow we got slides out of order. My apologies. So, we talked about mission planning on top of collection. So when we're talking about collection, probably the first thing and the thing that people, when we have a problem with the data, it's usually the telemetry, and it's usually how they've set up the base station. And I know we have a lot of good surveyors out there, but even they forget a few of the basics. And so when you look at that base station, first off, if you're looking at workflow, it should be the first thing that you put out on your site. And setting your base station, whether you're putting it on a monument that you've already pre-surveyed, or you're just going to set up your own internal network to do some of this GPS offset, making sure that you're clear of power lines, making sure that your vegetation isn't obscuring constellations, and that you're setting it up level, even though these seem very basic. They're the little getchas that we find time and time again. It's almost like when you can't find your computer to work and you haven't hit the ON button. It's kind of on par with that. And it's very simple, but it does happen. The next thing we talk about is setting control. And, hopefully you've set it out earlier, you have the time to do it. The biggest thing when you set out control, first off, the targets are a lot larger, but you only really need one per data set, depending on how much acreage you're going to cover. And that really is there as that final adjustment, so that you're getting rid of the local area offsets, and you're also clearing out any of the bias that you may have inside the inertial measurement unit. And people will tell you, oh, we've got this accuracy and we don't have any bias. That's not right. I don't care what people say. I'm always removing bias on multiple of the platforms that we've used. But also setting out control is another piece, and that is, a surveyor or a construction firm is going to want to know the quality of what you gave them. And, when we look at elevation quality, it will change from day to day. It's not like these sensors will give you an absolute perfect 5 centimeters, 3 centimeters every day, and it has to do with just atmospherics, sunspots, who knows, not enough satellites that day. So you really need to have a series of controls to not to adjust your data, but to validate your data. We talked a little bit about site surveys. Mostly when I do a site survey, it's looking at tree lines, finding obstacles, and validating my emergency action plan to make sure that I've identified all the things that could get me, and in the prior order of the likelihood of happening and the risk of severity. And then the last thing after I've done my site survey is really looking at my flight automation, because some of our systems have perception built in, obstacle avoidance. and that's nice to have, but you know, I never trust a drone. So I always, before I go launch and after I've done my site survey, go through my flight automation plan, my waypoints, to make sure that I haven't made a mistake, because a mistake is pretty costly. And we have a lot of folks that will buy a unit and then I get a call. It's like, well, can you fix it? and they didn't do a proper site survey. All right, so we talked about that. Post-processing, as we kind of alluded to, this is really the crux of the workflow, and this is what it differs. So here you're looking at, you know, this was a three-dimensional model that we had to do, so we did a grid. And so we're going to take all this data, the GPS data from the base station, the PPP, OPUS reports, and those corrections, if we're going to use that. Sometimes we do a comparison to validate the base station just to see how accurate we are. And then we'll have the GPS data off of the drone, or the payload, because our systems don't tie into the drone, and the inertial measurement units, and then finally the LiDAR data. And so we're going to take all of that and dump it into a file structure. And as we were talking about, when we're talking about the hardware, the first thing we're going to do is a telemetry correction. And what happens is, you know, your LiDAR is going off at about 1 sampling per second. And so if you're going really, really slow, you don't have a lot of distance in between there that you have to account for. However, we're going somewhere between 5 meters per second to 20 meters per second, depending on what you have to do, and maybe even faster for mobile on a vehicle. So it, for 1 second, could account for, you know, several hundred feet of unaccounted real estate in our telemetry. And so now we have to tie in the inertial measurement unit to segment that and take the GPS and weigh it against, or compare it against what the inertial sensor is actually sensing, and then through a little what we call smoothing, make sure that path is correct. And we can get that path down to about 2 centimeters of correction. You know, if we're doing a really good job, you know, that's how precise we're actually getting the position of the payload, i.e. the drone. From there, we'll export that to, you know, a compiler, and all that does is take all the different time hacks off the telemetry and combine it with the adjacent time hack from the LiDAR, and that's how we get an LAS point cloud. Now, mind you, we've talked through, and it sounds very, very complicated. For a VLP-16, we're talking about maybe 15 minutes till I have my raw LAS point cloud. That means I'm actually looking at my data right there. There's no 5 hours, you know, we're setting it up to a server to see if I've actually got the results. After that's done, after I have my LAS cloud, then typically I like to do register and bias. So this is where I add a little bit of that control. This is where I add metadata into the header of my my files, and I decide what size files I'm going to want to have. Reason why I bring this up is metadata is really important because it tells the next person, or it tells the software later what units of measure, what geometric standards or geoid standards you're actually using. And I'll explain this in the scenario, because this actually did happen to us, that they used the wrong standards. So making sure that, you know, basically the documentation inside your point cloud is correct is the final phase, you know, of a professional workflow process, and it will save you a lot of money. Okay. So the use case here, we're going to get into this. We'll spend about 15 minutes on this. You know, so what you're looking at is an artistic diagram of what they wanted to do. This was done outside Manassas, Virginia, for a transportation intersection expansion. And so we were asked to kind of do a proof of concept demonstration of what drone LiDAR technology could do, you know, versus the photogrammetry and that kind of stuff. And so the area that we're looking at here was about 20 acres. It was wooded. That was one of the concerns. And if we look at this diagram here, and if you can see my little cursor, the road is right here, but they want to get this overpass to change out the flow here, but they didn't want to to encroach on the property owners on the boundary. So they had this large wooded area that was elevated and this huge mound of dirt. And you'll see this in a second on the LiDAR cloud. And they wanted a really good analysis through the trees, mostly to figure out the cut and fill applications while they're getting ready to do the work. So they've already done a bid, and so they've already had some form of modeling, as you can see here. I think Doonesbury did this one. And so now they want that last as-is model, or that last topography to kind of refine their estimates and figure out what they had to do next. So not really sitting in the pre-bid phase, but really in the as-is modeling, getting ready to execute. So they're already marking up the roads. They already had all their survey points set up. And this was a good way to see what this technology could do for them. And so they wanted, when we look at the scope, and the folks that have watched a few of these with me, that I harp on, any sensor technology is great, but it's actually worthless if you do not know what your data requirement is. And so the first thing that I do, whether you're looking at a LiDAR purchase, a rental, services, or what have you, is I go right to, well, what is it that your customer wants to understand? And what is that product? And then we walk it back. And so in this particular case, they were looking just at the topography. They wanted, the basic elevations. And so with topography, the next question I usually ask is, okay, what level of contour do you want? And of course, everybody wants 1/10 of a foot, and that just doesn't happen. Oh man, sorry about this, guys. I don't think anybody needs to see my email. There we go. All right, so sorry about that. And of course they want 1/10 of a foot contours, which for those folks that are processing data and you're trying to push it across the internet is an enormous amount of information. And we'll talk about that a little bit more. And then they wanted what we call laser quality 1. So that is really a qualification of the number of points per meter squared. In this particular case, 8 points per meter squared. So that kind of sets up, if you're looking at USGS standards, FEMA, or I think even ASPERS has this, that's declaring kind of what the product should look like so that you can set up your collection plan. And then for classification, all they wanted was bare ground. And that means that we've removed buildings, trees, and anything except for the base topography. So that is your collection schema. And so that tells you how much work you have to do. What we didn't throw on here is what level of certainty or what level of quality. And I've only seen a few places talk about, a level 1 through level 4, with a level 1 being, auto classification. I'm okay with a little bit of noise. And a level 4 is I've gone through and used control points and manual surveys and data comparison to ensure that I actually have the ground. So there's different levels, and that will dictate the amount of post-processing work that you have to do. And then the last point here, and I guess there's some people in the room probably going, well, why LiDAR? Why don't we just put it on the back of the truck? Isn't that easier? And we'll talk about that more in detail, but yeah, it is, until you start running into some of the shortfalls that you have with mobile. And we're seeing, not just in Virginia's case, that was a nice intro use case, but we're seeing in Washington State and some other places, Caltrans is another, where they don't want just the berms. They want to see farther out. And so that runs into some interesting phenomenon when you're dealing with mobile that can mitigate it, but may not be as easy, where aerial is allowing them to see, a couple hundred yards out, so they can actually start to see things like, if you look up in this hill, looking up on the top of this hill and understanding how much vegetation they have to take out. Or if we're looking at this left side here where my arrow is, you can see at this field and figuring out, what is the runoff, and do we have to do any erosion mitigation or runoff mitigation to deal with the EPA and environmental concerns. The other piece of this is, we've talked about mobile, then we look at aerial. Well, aerial is only going to get you a finite set of points. And so maybe if you're dealing with this, in this particular case, they wanted something with more high fidelity, which LiDAR from a drone is a lot closer. We'll talk about that here in a few seconds. And then terrestrial, to do this same site would be about a day to figure that out. So, those are the comparisons of the different sensors, because your customers have options, and LiDAR on a drone is not the only case, but this is the case that they made of why they wanted to see this technology. So kind of following through in the workflow that we had outlined here, the first thing we had to do was mission planning. And you look at this chart, and this is what the site actually looked like underneath these overlays. That we had a hilly area up here to the actually to the east, which is to the top of your screen. And then at number 7, we had a knoll over there. And then if you look from 5 to 6, from the diamond 5 to the round 6, that was actually in like this sunken valley where they had drilled or dug through that saddle there to put in this highway. And so, these are just some of the elements that we had to work with. So the first thing when we did the mission planning is we wanted to look at the terrain. If we're in the middle of Kansas with some of our education partners, we really don't have to worry about hitting too much versus if we're going up to Michigan, where we have some rolling hills, but now we have 180-foot trees that we have to deal with, which cut our visibility, and we have to worry about those kind of things. So when we looked at this for the first piece, we're like, okay, what's the terrain, and how is that going to affect my ability to fly and stay safe and collect correctly? The other piece of this, when we looked at the terrain, because we all saw from the multi-beam, is, am I going to have any shadows cast? And if we looked at like point 2, if I had, let's say, if I had a sensor that could reach out further, I may not see the whole backside of this hill from 3 to 5. And so that would be casting a shadow. So I had to look at that. So when I set up my pattern, I'm making sure that I get everything that I'm supposed to. So that's the first piece. And by the way, these are kind of in priority order. The second thing we had to look at, was flight over people. And depending on where you're at, these folks weren't as bad. So we stayed within the FAA guidelines, which is, under, it's at the discretion of the pilot in command, but you can't fly directly over people. And since we're dealing with a M600, which is a little heavier and could have a higher fatality rate than, let's say, a Phantom 4, we did provide an offset. And luckily, this was an urban area, so we didn't have pedestrians, but we still had traffic. If we were dealing here in California with Caltrans, and then we had to completely offset from the road, mostly for their legal teams, and I think Herschel Phillips has a really good plan on how they mitigate theirs. Then the next thing we had to look at was, of course, obstructions in vegetation, more importantly, trees. And so that was a huge consideration, trying to estimate what the local vegetation was and how high these were going to be. And kind of tying point 3 and point 4 together, if you look down at the bottom here, this caught us off guard. We didn't see it in the imagery, but there was a large FM tower there. And so first we had the obstruction concern, which, we could figure out how high the tower was and figure out the stay wires and do a geofence offset. That was easy. Where it got interesting was, like when we did with Iraq, we get too close to some of these towers, it actually would put us in a position where we're lost communication. And so we had to look at this and go, okay, is this going to interfere where my drone won't stop flying? It'll go to the next fly to point until it times out. But now I'm opening myself up to liability of, I'm no longer in control of my aircraft. And as the pilot in command, that's a big no-no. So we had to look at that, and it turned out to be fine. And then we also had to add in, based on the size of the site, some emergency action points. So if I had a battery out or something was going wrong, these were the places that I was going to land as safe landing areas or ditch or crash if I needed to. So I always gave myself a place that I could mitigate in a worst case scenario. And that's what I mean by having that, looking at the site and understanding what your hazards are going to be. And then judging my pattern for what my accuracy requirements are, whether I'm doing a root mean square or I'm trying to hold a certain level of confidence, like a 95% level of confidence. And in this particular case, what's my vegetation penetration? We purposely picked off-leaf, even though we had a blend of deciduous and conifer trees there, so that we would get the most penetration for the topography there. But this may, as you'll see in a minute, may change how fast we go, how low we go, and just the very characteristics of how we're actually going to fly. And ultimately, a lot of these planning factors were really coming down to what point density do I really need to get through the vegetation to get me 8 points per meter squared once I've stripped everything else away. All right, so in this, as we showed, this is the visual diagram of what Frank showed you a few minutes ago. And, we used the chart because it's pretty quick, but you can see, we're looking at that topography. Was 20 meters realistic to be flying when the average height of the tree was about 40 meters? Probably not. Was 40 meters really realistic? No, we really wanted to have a buffer. So we flew at about 45 to 50. And as Dennis and those guys will tell you, we wanted to make sure, so we actually flew out the sacrificial Mavic just to make sure that we didn't hit anything with the flight plan that we had. But then the next question is, well, how much density? And so a lot of folks would go with, well, the slower is better. And yes and no. Slower will get you a really high data rate. That's fantastic. And if that's what your customer wants or that's what you need, do it and adjust your bid accordingly. However, time, rate, and there's price sensitivities. You may want to be flying, if you can achieve the results at 11 meters per second, so that's double the rate. But now instead of 20 acres, you're getting 40 acres done. So, understanding how this chart works and the point density to get your end deliverable is really important. And because really, in the ultimate, it's not, nobody really cares about this technology. They care about what you're going to charge them and the results you're going to get them. All right, so we talked a little bit about field setup earlier, actually went into a lot of detail. But here's some lessons learned that we had here. First, working directly with that survey team and finding your survey points. We got out to the site, I think I had, because we were teaching at the same time, I think I gave myself 5 hours, but really it should have taken me about 2 hours, for a small site, just for the setup and taking my time. And ultimately, if I didn't have a base station, it would have been done in probably about 30 minutes. However, it took us 2 hours to find the survey pins. They had done a wonderful job at laying them out. They were done the year before, and the mowers and the crews, took out every pin or every marker that they had, and we had to walk around on our hands and knees to go find these things. So having your survey team there would have been very helpful, or having them prep the space so that you're not wasting time. Setting up the base station took us a little bit of time, not so bad, but then again, finding that right space that didn't have the power lines, as you can see here, and the obstructions was a big piece. Managing traffic, that's kind of a given. We had to have folks that flagged stuff out, and it was not so much, well, the takeoff and landing, that's a given, but it was also when we were in the low hover, that folks will be seeing this, and they're not focused now on driving. They're focused on the drone that's out there. Oddly enough, when we're up at 50 meters, nobody even knew we were there. But when you're down low, managing that traffic pattern, kind of like everybody's rubbernecking and watching you, which is a problem for the drone, but it's also was a safety issue for our crew that was actually managing all that. And then determining visibility, as we talked about, I actually had to move and shift around the site to make sure that I maintained visibility. Now moving on, talking about managing the takeoff point, we kind of talked about that briefly. Managing your safety teams, making sure that your safety teams and your safety observers really kind of knew what was going on. We had a radio comm set up, we had procedures established. You really kind of need to do that for this kind of work. And again, talking about how do you manage the traffic and people flow into your site, because you can't plan for everybody. And even though you can't fly over folks and you're trying to manage yourself in scarcely populated areas, people do show up, and so we had to have a plan for that. We didn't have any people on the site, but that was still an issue. And probably the last point I'll break out here is something we hadn't considered. Most drone guys know that in the fall you're flying over released up in the Northeast over a tree, and you're going to get a million baby robins coming out attacking your bird. We kind of had the same issue happening there. We had a series of eagles or condors, and we kind of had to make a call on, are we going to risk this wildlife, or more importantly, we're going to risk the drone too. So it would have been a double whammy. And so we had to add that to our emergency plan on what we were going to do there. Just as kind of a side note. Okay, so now that we've talked about drones, let's talk about what really matters here. Let's talk about the raw data. So we'll take another 10 minutes. We're going to run a little bit over. Sorry about that, folks. So this is the raw data. This has not been cleaned, modified. I kind of really firmly believe in showing a customer what comes directly off the bird and then how they can improve it from there. So this is totally right off the bird, unclean. And so you can see we got a pretty good set of density, and you can see all the markings and lines, and you can see right through the trees. And you can see we have some conifers and then our deciduous trees going on here. So it's just a quick representation of this is what we saw coming right off the bird. And that was the intersection that we were doing. We actually had operations based out of over here in the, where my cursor is. That's where we sit. And then I maintain visibility walking to and from so I could have both of these corridors. All right. So probably the first thing, even though we were doing topography, I had a data team come in and work this for us as a side just to kind of show the capability. You're going to have a lot of folks coming in as, well, I want 1/10 of a foot, or I want half a foot, or what have you, and ultimately they're all going down to line diagram, especially in the construction industry. And so understanding that this is the product, and how did we get here? So once we took that LAS cloud I showed you, all we did is an auto classification to go to ground. We did have to do some cleanup to get rid of some pitting and some visualization and smooth out the surface. And then we brought it into a regular CAD program. Those folks that take our course, we kind of talk about this and just do straight up line work inside of CAD. So this is a very easy process once we get from LAS cloud to a digital elevation model or a vector map, and then we get it into a CAD model. The software is pretty easy to go. This is a little intensive getting your lines in, but that's going to be true if you're doing photogrammetry or Lidar. Okay. Another place that I kind of want to point out is power lines. We'll have folks come in here and saying, hey, a Velodyne can't see a power line. And you saw Frank's model with the, I think it was an HCL32, showing power lines. But as I alluded to earlier, knowing how to fly that equipment is important. And this is something we cover in our course is, that's why I annotated where the flight path was. But if you look at this data, yes, we have really good point density on the line, but we even have it all the way back. And you don't need a lot of points to estimate a line. But why did they want to see this? And it's important, like when I did work way back before I joined the service, I was a layout engineer, fresh out of college, laying out pipeline, working with the field engineer. And, if you have large earth movers, they're going to probably be up over these power lines. So knowing what these measurements are going to be to make sure that, your earth movers and your dirt workers are going to be free. Otherwise, they're going to have to add this to the bid to move it. So that's why they're going to want to see these overhangs and crossovers. And so my point here is knowing where to put your drone so that you're getting the maximum amount of sensor coverage is important here. So you can see here's the cross path, and here's our side look at that. All right, the other piece is field grade information. So again, the reason why the drone was probably the preferred method, even though this was a small site, and it was only 20 acres. And mind you, it only took us 20 minutes. No, it took us 15 minutes to fly this. So we were in and out of the site, in theory, pretty quickly. But if we were using terrestrial LiDAR, we would have only gotten this slope here. And they wanted, again, up over the top for all this vegetation. But again, what they want, even for mobile, is they want toe to toe and then down the heel, so they figure out the cut and fills in this area here, because they're going to have to remove dirt and shape the space. All right, and then the most obvious is cut and fill. And for the folks in the room, photogrammetry is probably way easier for volumetrics until you have vegetation on top, or you're dealing with a large site. And so here we had grass. It wasn't that big. We would have been off by about 6-7 inches based on the grass there if we had used photogrammetry. But the biggest thing is we were able to get on the volumetrics probably within 2 hours of getting back. I mean, you know, that's a relative measurement. It was really easy to do. So for jobs that have large sites and need that information quickly, LiDAR still is the better way to go, because you're going to have that information in the field right then and there. You're not sending that information somewhere else to get processed into a model. But again, for price point, if you can wait, yeah, photogrammetry is the better option. But we have to kind of show this case, you know, because there are customers that just can't wait, or they have such large sites that they need to be efficient. And so that's what this point was here. All right, so vegetation penetration, the whole crux of this, you know, you can see we have some trees with leaves on it. So these were our conifers, but then you can see the deciduous also. And we have all the way under both canopies there. I think when we did the final analysis, I think we got something like 10 points per meter squared on there. And we had to vary the resolution a little bit just based on the second canopy. We had a little bit of pitting, but again, with a little bit of smoothing, we still were able to maintain that 1 foot contour, which is exactly what they wanted. And then here's another example of the side of here where you can see that we had gotten through here very nicely. You know, so if you can collect off leaf, it's probably preferred. It's, but you know, again, you can still get penetration, so it just depends. Get that going. And I'm running out of time. All right, so you know, since this was a road, I'm going to give you a side of the road, and really these types of measurements are not so much about the absolute accuracy or the accuracy in reference to the Earth's geometric system. This is about relative accuracy. How accurate was the sensor? And you can see here, when you look at the statistical model, we're within 0.2 of a foot, which is about what you would see from a VLP-16. And you know, so some folks are going, well, that's not good enough. And we've had some folks, large construction companies that we work with, you know, they're trying to get 21 millimeters. And we understand that, but then you have to understand the level of precision that you're looking for is going to increase the rate. And most applications that are out there, you know, are going to fit within this 0.2. You know, even the surveyors that want down to 1/10 of a foot, you know, they can still do their manual points. They just don't have to do as many in their survey line, and they can augment with this. And since they know that they're 0.2 off, can add that to their model. So it doesn't replace the surveyor. The surveyor is still going to have to do some lines. They just don't have to do as many. And this is kind of what this was doing. You know, the surveyor actually validated the data, and that was what was good here. And again, you know, the reason why you use this is vegetation, you know, and so here we have roughly about the same thing. We have about, about 0.2 in here as we're able to, but we have a real clear estimation of where that ground was. And that's what's important, you know, how clean this was. And so again, we thought this was a really good case, especially for the type of sensor and for the return on investment that you get here. And then lastly, you know, we had, I think, 5 points that we were given. You know, I know Asper's asked for 20 for a job site this small. It really wasn't beneficial. But you can see at the very end, you know, we were within 5 centimeters absolute. And so that was a pretty good result. So customers really like that. A lot of information. And I know there's lots of questions, and we're actually well over time here. Sorry, I try to add as much value to these as I can, but write these down. So first off, if you want to talk about the value, or you have an honest question, hit us up at info, and either Dennis or I or Linda can talk to you about getting the answer to your question. And if you're social media savvy, you can hit us on Twitter. You know, I'll post those both in Twitter and up on YouTube to answer your question in a video, because I like to share with the entire community and get the.
Okay, we hope that you have enjoyed this presentation and that it best serves you. If you would like to see something new, another business case or another partnership with another sensor, go ahead and leave a comment down on the bottom. And if I get enough comments, I will definitely go out there and do another use case, something like this. Finally, just to stay up to date on what we're doing, don't forget to subscribe. That way you're staying in touch with everything that we've got going on. And finally, with that said, is if you want to learn how to do professional LiDAR using a drone-based system, go ahead and check the next video up here in the top, and that will give you all the information to link up with us in some of the advanced programs and projects that we have going out today.